Hello guys. Today this video is about conservation of energy and example problems in the English units. So this is conservation of energy, and before we go ahead and solve those three problems, just want to point out first what is conservation of energy, what is the law of conservation of energy, and it just states that energy is neither created neither created nor destroyed. Okay? It is simply transformed into other forms of energy. Okay? So knowing those principle, we will come up with an equation which is the energy that enters the system would be equal to the energy that leaves the system. Problem number one, I would paste that here. Okay. So assuming that there are no heat effects and no frictional effects, find the kinetic energy and speed of a 3,220 pound body after it falls 778 from rest. So we will start with the energy flow equation or steady flow energy equation and delete terms which are irrelevant. So that is always the case for every problem. No? We start with the energy flow equation. So let's write that down. You always start with this one. Okay? And you would afterwards delete unnecessary terms or terms that are not considered in the problem. Say for example, in this case, we don't have our internal energy, we don't have our workflow, and we also don't have the heat. No? Sabi dyan, no heat effects, so we don't also have our work. So we have P1 plus K1 and then is equal to P sub 2 plus K sub 2. Let's write the formula for P sub 1. So that is mg h sub 1 over K plus kinetic energy of the body would be mv sub 1 squared over 2K. Okay? And then at point 2, that would be mg h sub 2 over K plus mv sub 2 squared over 2K. So our body, let's say this is the body and this would be the cliff. No, let's just assume that there's a cliff that the body would fall into. So the height is 778 feet. No, and then the mass of our body is equal to 3,220 pounds. So what we can see here is that it starts from rest. No, so therefore at point 1 the velocity is 0. So v1 is equal to 0, then therefore we can cancel out that term. Also, h sub 2 is equal to 0. No? H sub 1 is equal to the total height, while h sub 2 is equal to 0. So, cancel na rin to. So, we now have mg h sub 1 over k is equal to mv squared over 2k. Okay? So, we can still simplify this. We can cancel the mass. We can also cancel the proportionality constant and arrive at the formula for V. So that is equal to 2 times G H sub 1. So let's go ahead and input those in our equation. So V is equal to 2 times G is 32.174 feet per second square. That's the gravitational acceleration, and the height is 778 feet. Okay? So if we multiply the units, we have feet over second square, and since it is going to be in a square root, or it would be raised by 1/2, then the final unit will simply be in feet per second. So let's go ahead and do that with our calculator. So 2 times 32.174 times 778, then we get the square root. So 223.75. So that is the speed of our body when it falls down. Okay? And then what is the kinetic energy as it reaches this point, no? So we have point 1 here, the point where it is resting, and the point 2 where it falls down. Okay, so what is the velocity at point 2? That is 223 feet per second. What is the kinetic energy? So kinetic energy at point 2 will be mv sub 2 squared over 2k. So the mass is given 3,220 pounds. V sub 2, we have just solved that, 223.75. Let's write the unit, feet per second. And then we square, then 2 times k. So since this is in pound mass, okay, the mass, of course, that is in pound mass, we will use k as, the k that we will use is 32.174 pound mass feet over pound force second square. So what will happen with our units? We have here pound mass, of course pound mass cancels out. Here we have feet square over second square, and then second square will cancel out, feet will also cancel out, but there will be a remaining feet, no? So our unit is pound force feet. Pound force feet. Since pound force feet is not the appropriate unit for energy in the English system, which the appropriate unit is BTU, we will use the conversion. 1 BTU is equal to 778 pound force feet. Okay, so let's go ahead and calculate that. So we have 223. Let's square that again and multiply 3,220 and then divide 2 times 32.174. Okay, so the answer is 2,500,160. And then that is in pound force feet, so let's divide 778. So the correct answer, or the answer for the kinetic energy, is 3,220 BTU. Okay, that is our kinetic energy. So let's go ahead with our problem number 2. Hope you are getting a technique, no, in solving. So problem number 2. So we have reciprocating compressor draws in 500 cubic feet per minute of air. So let's illustrate that. No, let's try to illustrate that. We have a compressor. It has, let's say, this portion as our inlet, and this is our exit. Okay, inlet, exit. So let's say this is point 1 and point 2. So at point 1, the air that comes in, so that is volume flow rate. So 500 cubic feet per minute. Okay, and then the density of the air that's coming in is at 0.079 pounds per cubic feet, and the density as it is discharged is 0.304 pounds per cubic feet. Also given the pressure at the entrance, 15 psi. So the A there signifies that this is already absolute. Okay, P sub 2. Remember that pressure and temperature should always be absolute when solving problems such as this one. Then we have delta U. So there is an increase, no? So if there's an increase, then U2 must be greater than U sub 1. And that is equal to 33.8 BTU per pound mass. Okay? Determine the work in BTU per minute and in horsepower. Okay? So if we will go back to our equation for solving work, then we will have Q minus delta P minus delta K minus flow work minus internal energy. Okay, we don't have our potential energy here. We could neglect that, and we can also neglect the kinetic energy. So we just have the workflow, the change in workflow, and the change in internal energy. So the quantity or the term that we will solve here is simply the change in workflow, which is workflow 2 minus workflow 1. And workflow is pressure times volume. So in this case, we're given specific energy BTU per pound mass. So therefore, we will simply use this specific volume. Okay, so this will be P sub 2 V sub 2 minus P sub 1 V sub 1. Okay, so pressure is for pressure 2, it's 80 psia. That is pounds per square inch. Specific volume, so we're given the density. So specific volume is 1 over the density. So 0.304. Now this would be cubic foot per pound mass. Okay, this is pound for, so you cannot cancel that. So first we will convert square inches, 144 square inches to square foot. So cancel to class. Cancel yan guys. Cancel din yun. And then we now have pound force foot per pound mass. And as I've told you, the correct unit is should be BTU. Okay? So again, we apply the conversion factor 1 BTU per 778 pound force feet. Okay? So cancel tong pound force, cancel din yung feet. And we now have BTU per pound mass. Okay? So we will subtract that with the pressure 1 times specific volume 1. Pressure 1 is equal to 15, so I will not write the unit anymore. Then 1 over 0.079, because I have explained the cancellation of units in P sub 2 V sub 2. Then we will multiply 144 over 778. Okay? So we can simplify that. No? We can simplify this one by factoring out 144 over 778. And then we have times the quantity 1 over or 80 over 0.304 minus 15 over 0.079. And the unit that would be left here is BTU per pound mass. Okay? So go ahead and solve the change in workflow. So I have 80 divided by 0.304, then minus quantity 15 divided by 0.079. Then let's multiply 144 and divide 778. So I have 13.56 BTU per pound mass. So we now have everything that we need to solve this problem. Again, work is equal to Q minus delta U minus delta WF. Okay, that's our equation here. Since Q is negative, no? Since Q, so sabi dun sa problem, again, the heat is transferred from air, so therefore Q is negative by cooling. So 13 BTU would be minus 13 BTU per pound mass. Then minus 33.8 BTU per pound mass. Then minus 13.56 BTU per pound mass. Okay? So the answer is negative. No? Obviously, it's negative. Why? Why is it negative? In the problem, it's already stated, no, that we have to determine the work on the air. Now, if it's work done on the system, then that would be negative. If it's work done by the system, then that is positive. Okay? So work. So the negative sign is just a para sign convention. So now have, you can just simply add 13 plus 33.8 plus 13.56. So negative 30.36 per pound mass. Okay? But we are not required to get the work in BTU per pound mass. Instead, we want to solve the work in BTU per minute and in horsepower. So what will we do? We are given the volume flow rate and the density at point 1. So from that, we will first solve what is our mass flow rate. If we multiply our mass flow rate with our work, then the resulting unit would be in BTU per minute. So mass flow rate is equal to volume flow rate times the density. So 500, volume flow rate is 500 cubic feet per minute multiplied by our density 1, 0.079. Let me just check. Okay, 0.079 pounds per cubic foot. Okay, so cubic foot will cancel out and we have pounds per minute. That is the unit for mass flow rate. So 500, move this, 500 times 0.079 and 39.5. 39.5 pounds per minute. So as I've told you to compute for the work in BTU per minute. So we have 60.36 BTU per pound mass. We multiply our mass flow rate, 39.5 BTU per minute. So pound mass here cancels out. And the unit will now be in BTU per minute. Okay? So 39.5, sorry about that. 39.5. 39.5 times 60.36. Okay? So the answer is 2384.22. 2384.22 BTU per minute. Okay? So how about the work in horsepower? So we will have a conversion, and that is the conversion of BTU per minute for a horsepower. So 1 horsepower is 42.4 BTU per minute. Okay, so cancel to, and then we have horsepower as our unit. So 2384 divided by 42.4, so 56.23 horsepower. Okay, so that is the work in BTU per minute and in horsepower. Okay, so last problem for the English unit, the English system for conservation of energy. Okay, so problem number 3. This is a simpler problem than the previous problem. No, steam enters a turbine with an enthalpy of 1292. So that is H sub 1, 1292 BTU per pound mass, and leaves with an enthalpy of 1098 BTU per pound mass. The transferred heat, so yan na naman tayo, transferred. So therefore that is negative. Kasi transferred eh. Heat was removed from the system. What is the work in BTU per minute and in horsepower? So the same. But we're now given the mass flow rate. So 2 pounds per second. Okay? So here we're introduced with the concept of enthalpy. So enthalpy, that is simply equal to internal energy plus the workflow. So plus PV. So therefore, if we are going to solve for work, and we know that work is Q minus delta P minus delta K minus delta U minus delta PV or delta WF workflow, then work will now be Q minus delta P minus delta K. Then this two would be replaced by minus delta H. Okay? But in this problem, we will neglect the change in potential energy and the change in kinetic energy. So work is simply Q, so minus 13 BTU per pound mass minus delta H. So H sub 2 is equal to 1098 minus 1292. So both are in BTU per pound mass. Okay? So work is equal to, so 1098, so that would be negative, but since this is also negative, then this term would be positive. So we'll just go ahead and do 1292 minus 1098. So that's 194, and then subtract 13. So we have 181. So similar to what we did with our previous problem, we multiplied the mass flow rate. So that is 2 pounds per second. But we want to get the work in BTU per minute. So convert 60 seconds to minutes. Oh, convert seconds to minutes. So the conversion is 60 seconds equal to 1 minute. Okay. So 181 times 2 times 60. So 21,720 BTU per pound mass. Okay. So that is the work, or BTU per minute, I should say. Okay. Let me go ahead and cancel the units dito. Cancel yan. So BTU per minute. Okay. How about the work in horsepower? So again, we will convert. So multiply 1 over 42.4. Okay. So cancel to class. Horsepower would be left. And the work in horsepower, we simply divide the answer. Okay. Kamali ako lagi ng click. Divide that by 42.4. Okay, so the answer is 512.26 horsepower. Okay, so the work is done by the system here. Okay, or the work is done by the turbine. So the turbine, so in other words, a turbine generates power of 512.26 horsepower. Okay, so I hope you learned something from this short video, and stay tuned for the video of conservation of energy, but with example problems in the metric system. Thank you for watching.